We're going to cover in the realm of regression analysis the concept of what we call a prediction interval. This is actually the first topic that you get to in regression. I think that's really difficult to truly understand. It's not because it's hard. I promise you in 10 minutes it'll be really easy for you. But the problem is that it introduces some ideas. It's just really easy to get confused as to what they're actually talking about. So we're going to take it step by step, and we're going to start by looking at this simple graph that I've drawn here. But I'm going to warn you, I've got to talk a lot, and I'm probably going to write a lot more than usual here. And I hate that, but I have to do it. But at the end of it, you're going to understand exactly what a prediction interval is. All right, so here's a basic regression line for some data. The example I want to keep in your mind as we talk about it is the age of a house versus how many repairs per year that house has. It stands to reason that probably young homes have smaller number of repairs per year required, and the 20-year-old homes out here have a much higher amount of repairs per year. We're not saying that one causes the other, it's just saying it's something I would probably expect to have happen. Now, I want to ask you, first of all, what do we have here? We have the raw data. This is the age of the house versus how many repairs a year that we have. We have this different data here. And then through that, we calculate the equation of the regression line, and we write the regression line down. And don't forget, what does the regression line look like? As an equation, it's y hat is equal to b naught, which is the y-intercept of this line, plus b1, which is the slope of this line, times x. Now, the whole point of regression, it's really important for you to understand what is the point, okay? You see, we've sampled this data. We know what this data is. We have, what, maybe 10 points here or something like that? I haven't really counted them up, but there's a handful of points that we've collected, maybe in our block or our city that we're studying. And we know what the repairs per year of these points are, right? And from that, we draw a line through there, and we say, yeah, this is a pretty good line that goes through there. And we label it y hat. You might have been thinking, why did we label it y hat a long time ago? Why didn't we just call it y? It's basically because y hat is a sample statistic. Remember a long time ago we talked about standard deviation and variance and things like that. And we said, for instance, the standard deviation, let's talk about the standard deviation for the population was sigma, right? But this was a population parameter. But when we did our calculations, we calculated the standard deviation, which was S, right? These are basically, the two ideas are basically the same. It's just that when we calculate using small sample sizes or sample data of any kind, we use the letter S to remind us that we're just talking about a small subset, maybe 100 people or 500 people. But in statistics, the entire point of it is to take samples and figure out how we can draw conclusions about the population. So the population standard deviation is called sigma. We never know what that is because we can't sample 300 million people in the country. It would take too much time and money. But we take a look at the sample standard deviation and we try to link it and try to draw conclusions back to the population standard deviation. It's the same exact thing here. This regression line goes through the data, but it's a sample statistic because this entire equation, this entire regression equation, this B0 and B1, it was calculated just from these handful of data points, right? So when we label it y hat, we're just reminding you that, hey, this regression line comes from the sample data. If I were to do this whole process again and ask 10 different homeowners with different age homes how many repairs per year they have, then I would get different answers, very slightly different answers for all these data points, and I would then calculate a different regression line. It hopefully would be pretty close to the one that I have here, but it would be different. What if I go to a different city, like somewhere in Florida instead of somewhere in Colorado? I'm going to probably expect different values for these points entirely, so I'm going to get a different line. So the point is, I'm kind of trying to give you the big picture, is that this regression line is really only as good as the sample data that you use to collect it. But more importantly, we're always more interested in what the population is doing. Remember, what is the point of regression? We calculate this line based on this data. Why do we calculate a line? Why do we even care? It's because we have points here and here and here and here, but we don't really have any points here. So this line is kind of useful as a starting point to go and say, well, let's say this here is, a 7-year-old home, and over here, this point of here, or let's say this point here corresponds to, like, let's say a 9-year-old home. So our sample data says that for a 7-year-old home, we have some points here, and for a 9-year-old home, we have a point up here. So we kind of have some data to tell us how many repairs per year those houses require, but we don't have any data at an 8-year-old house, right? So how would we best estimate how many repairs to find for an 8-year-old house? Well, we would just calculate it based on the line. We'd plug in the value of x is equal to 8 here, and we'd calculate based on what we have. We would get the point on this line, which we would then read off and say, well, it's however many repairs per year. But again, this line is only as good as the sample data we started with. In real life, the population of all the homes in America or in the world would have millions and millions and millions of data points, and they would have a line, a regression line that would go through that. We can never know all of those data points, and we can never know those lines, right? But we can use as a starting point the regression line that we have to kind of calculate things in between data points or to get additional information about the points that we have. Okay, so now I need to unfortunately start writing a few things down. The first part is the line, the regression line. The regression line is and you should recognize this term because we've talked about it before, it is a point estimate. And when I say it's a point estimate, I mean it's a good starting point to go and look at other points along the way and say, well, what does the line say? It says we should be about here. But you should keep in mind that line is not truth. It isn't truth because you can never know the truth because you can never measure every home in the country. You don't have enough time or money to do it. So you just, as a starting point, you say, well, the line's a pretty good starting point estimate, but it's just a point estimate. It's not the 100% guaranteed truth. I mean, you got to agree that if you go up to 8 years and read this value off, let's say this value was 5 repairs per year, that number is not going to be true of every home, every 8-year-old home in the country. It's not going to be true of every 8-year-old house. It's just a good starting point. Okay, so let's say we wanted to investigate and drill down a little farther into the 8-year-old house. How many repairs per year would it require? Based on the line, we would read off whatever the value we would have. But it's just a point estimate. Sorry, I'm reading from my notes to make sure I cover everything. But here's the punchline. What if I go and find 100 different people that have 8-year-old houses? And I ask them, hey, how many repairs per year have you had to do on your 8-year-old house? And I don't do this 1 or 2 or 3 times. I do it 100 times, or maybe 1,000 times, or maybe 10,000 times, 10,000 different homes that are all 8 years old. Do you think I'm going to get the same answer? Of course not. I'm going to get hopefully something pretty close to 5, if this is regression line was telling me 5 repairs per year, hopefully, but not necessarily. Some people are going to have much higher amount of repairs, maybe 10 or 20 repairs per year, the really unlucky people, and you're going to have some people that aren't going to have any repairs or maybe just 1 or 2 repairs. And hopefully somewhere in the middle, hopefully is where our regression line for our sample data is. If we've done a good job sampling, hopefully it means something. Okay, now graphically, I want to show you what that really looks like. This graph that I'm going to draw here really is the punchline of what I really want you to understand in this section. The age of the home versus repairs, repairs per year. All right, so forget about the sample data. I'm not going to draw the sample data again, but let me go ahead and draw that regression line again. And let's say this is around an 8-year-old house. All right, we already said that if we ask people with 8-year-old homeowners, you know, some of them are going to give us an answer that happens to fall right on our regression line. Some of them are going to have more repairs per year that they've needed, and some are going to have less repairs per year that they're going to need. All right, let me turn my little deal sideways here and try to draw something for you. Let me draw a little dotted line just to kind of intersect up here. So what we really are going to have is you're going to have kind of this normal distribution centered about that point right there. See if you can look at that sideways. This is kind of like a normal looking distribution that is shaped like a bell curve, and it's kind of centered about the point of interest that I care about, in this case 8-year-old house. Okay, so remember, this is the difference between sample data. This is truth. This is sample data. I only have 10 points here. I drew a line through it. Okay, I don't have any data at 8. Okay, but I want to use this information to go and figure out what would happen if I ask 100 people with an 8-year-old house. And what you're going to find out is that some of the people are going to require more repairs. They're going to be up higher than the line. But notice that it tails off. So fewer people are going to require lots and lots of repairs. And some people are going to have very few repairs, but notice it tails off down here. Very few people are going to have 0 repairs, for instance. And most of the people, which is the bulk of this curve, is going to probably, hopefully, if we've done a good job with our regression line up with what our regression line says. All right. Now this is true of the 8-year-old house, obviously. But let's say I'm looking at other data. Let's say I have some data right here for a 7-year-old home. I only have 2 data points from the data that I collected. But if I go to the population and I go to the entire population of the country, again, not the sample data, the population of the country, and I go try to ask as many people as possible, if I could know all of the population data of, let's say, 7-year-old homeowners, then I'm basically going to get a similar kind of deal. I'm going to have something that looks like this. I'm going to have a bell curve, basically a normal distribution, normal looking distribution that's going to be centered. I'm not doing a great job about that, right? What if I go ask people with 3-year-old homes, right? And when I say I'm asking them, I'm talking about the population of the country. If I could ask everybody, then what I would expect is to have a normally distributed set of answers around this guy. So you see everything here, there's basically a normal distribution here, a normal distribution here, a normal distribution here, and basically for every point, for every independent variable I have, no matter what the age of the house is, if I could know the population data, or if I could go ask enough people where I thought I had everybody in the population, I should get a normally distributed curve where the maximum hopefully sits on top of my regression line from my sample data, and it tails off as I get farther away in each direction. I think you can understand that the 3-year-old homeowners, some of them are going to be on the line, some are going to have more repairs, some of them are going to have less repairs, and so on. All right. This guy, this concept here, is called, it has a name, it's called a bivariate normal distribution. It doesn't really matter too much if you really remember that it's called a bivariate, but it has a word that's called bivariate normal distribution. It's called bivariate essentially because at every point on the independent variable axis down here, I have another normal distribution. So the normal distribution kind of depends on more than one variable, right? It depends on the actual normal distribution itself, but it also depends upon where you're looking. So that's called bivariate normal distribution. Let me make sure I've said everything that I need to say here. Probably the next most important thing I want to really point out is at the center of this bell curve here, let's take this point up here actually. If we extend this one back all the way to this axis here, the value that we're going to get is y hat, because this is the point right here that actually falls on the line. And remember, my line is governed by my regression equation, which is y hat. So every point on this line comes from our sample data, or is calculated from our sample data. We call it y hat. So this value is called y hat. Y hat, it's important for you to remember, is what we call a sample statistic. It comes from a calculation that comes from our sample data. But the value of y, which in just a second I'm going to teach you about the difference between y and y hat, this is a population parameter. The value of y that I'm talking about are all these possible values people could answer to me if I could know everyone in the population. If I could go and ask everyone in the country with an 8-year-old house how many repairs per year, some would answer 15 per year, some would answer 10 per year, some would answer 7 per year, 6 per year. It would form a normal distribution like this. All of these values that I get back from the population, they don't have y hat. Y hat are only the values on the line here. We just call it y. It's a population parameter that comes from this guy. The other thing I want to point out to you is this guy right here, this normal distribution, is basically a confidence interval. This is essentially a confidence interval. Because remember back, confidence intervals we studied in great detail a long time ago. Basically, the idea of a confidence interval is you take some sample data and you use it to predict what the population is going to do. And you say, hey, with 95% certainty, I think the population is going to be between here and here. That is what we call a confidence interval. We're 95% confident. That's where the word confidence comes from. And the interval means you have a range that you're saying the population is going to fall between. That's what we're doing here. We start as a point estimate, and also that's where we introduce the concept of the point estimate. We're going to introduce the concept of the point estimate as a starting point in the middle of our confidence interval. But we also recognize that the population might give us answers higher than our point estimate and lower than our point estimate. So the endpoints of the confidence interval at 95% confidence or whatever it is, that's going to be called our confidence interval here. But in the realm of regression analysis, we don't usually call it a confidence interval. We actually call it a prediction interval. I told you I was going to have to write a few things, and I'm sorry about writing a bunch of stuff down all at once. But basically, we call it a prediction interval. It's exactly the same thing. The concept is we take some sample data, we calculate a regression line through the data. Now we want to make some predictions about what the population of the whole country might say. We can never know what they're going to say, but we want to make some predictions. So we might say that we're 95% certain that respondents with an 8-year-old house across the entire country will answer between this many and this many repairs per year. That's an interval with a 95% level of confidence. We call it a prediction interval. So you see, when we're talking about prediction intervals in regression analysis, we're not talking about the sample data at all. We're making predictions about what the population is doing. Remember, that's the whole point of statistics. We take sample data, calculate something, and we predict what the population is going to do, what they're going to say. That's what this prediction interval is. Now, it's time for me to clear the screen because it's getting messy. Even I can see that. So I need to go off and actually write down what this prediction interval is, and we'll circle back and tie it all up in a bow in just a minute. So we have this concept of a prediction interval, which is a confidence interval. And we studied confidence intervals before, so if you don't remember what it is, go back and review my lessons on confidence interval. Basically, you have to start somewhere in their interval. And the center part of it is called a point estimate. And we just basically are going to use the regression line to be the middle of our point estimate, essentially. So what we say is that the respondents at a national level for the entire population is going to give us a value of y. It's going to be less than whatever is on that regression line as our starting point plus some margin of error, and it's going to be greater than whatever our prediction is because of the regression line minus some margin of error. And you can write that two ways. You can write it with less than signs like this, or you can write it just simply with parentheses, y hat minus e, y hat plus e. This is the concept of a prediction interval. Now, keep in mind that basically you start at a point estimate, y hat, you subtract something which we call a margin of error. That's going to give us the lower bound of our prediction interval. And then we take the same point estimate and we add the exact same margin of error to it to get our upper bound. Let's make sure that that makes sense based on the drawing that I just made for you a second ago. Basically, we have a regression line through our sample data, just a very small subset of our sample data that we've calculated. And at every point here, notice I've drawn this thing where the center of the answers that you get back from the population all fall on the regression line. Some people are going to answer higher, some people are going to answer lower, but right in the middle should be the point estimate. That's what we call a point estimate, is y hat. That comes from the regression line. So when you construct your confidence intervals or your prediction intervals, first thing you're going to do is find the regression line, figure out what the point is on the line. That's going to be the center of the prediction interval that you have. Now you take that point estimate and you add something called a margin of error to it. That gives you the upper bound of your prediction interval. And you take the same value on that line and subtract this margin of error, and that's going to give you the lower bound. And then you can say with 95% confidence that the population is going to give us a range of values between this and this value, whatever it happens to be, with a certain level of confidence. That is exactly what we did when we did confidence intervals. So if this is foreign to you, go back there. Now the next thing I want to do is write down this equation for, you need to know what the margin of error is. Unfortunately, it's kind of ugly. So the margin of error E is given as follows. Let me write this up here. Let's see, margin of error. And we're going to call that E, okay, margin of error. It's equal to, let me just kind of write it all down and then we'll kind of get going with it. It's T sub alpha over 2, that's a T distribution, times or multiplied by the standard error of the estimate, which you just learned how to calculate. And then I got to write a few things down here. It's going to be easier to write it like this. 1 plus 1 over n plus, and then we have n times x naught minus x bar squared. That's all in the numerator. The denominator is going to be n times sum of x squared minus sum of x squared. Now, if that's not enough, check this out. You take this giant thing and you put a square root around the whole thing, like that. not too great. In fact, I'm really bummed that I accidentally intersected the number 2 there. But I think you can still see what's going on. So this is the margin of error. It's ugly. That's why I started out showing you what the prediction interval is, so you can understand conceptually what you're doing. All you're going to do is you're going to use this equation to calculate a value. And I'm going to go over it in just a second to show you how you get there. Once you get this margin of error, you just add it to the point on your regression line and subtract it from the point on your regression line, and then boom, you have a confidence interval. All right, so let's pick apart what all these things are. The easiest things first. N is just the sample size. Anywhere you see N is the sample size. So if you have 10 samples, you put a 10 there. So this would be, 1 plus 1 over 10. 10 would go here, 10 would go here, okay? Now, X naught is the value I'm interested in. In the previous part here, I was showing you, hey, what happens whenever you take a look at 8-year-old homes? This is the X axis here. I'm interested in the calculating a prediction interval for people with 8-year-old houses. So in that case, we say that X naught is equal to 8. Okay, so this value here, X naught, is equal to whatever value I'm interested in. X bar is the average of all of the X data points that you have. That's why it's called X bar. Sum of X squared means you square each one of those X values and you add them up. This guy means you add up the values of X first and then you square them. We're going to do all this stuff in Excel in a few minutes when we have an actual problem, but that's what all of this stuff basically means. Square root is obviously a square root. Now over here, you're multiplying the value of what's under the square root times the standard error of the estimate. Now let me remind you, the standard error of the estimate, we already know what it is. It's the sum of y minus y hat squared over n minus 2. And remember, it's basically the standard deviation of how far apart your data points are from the line. That's what it is. But notice in the bottom, there's n minus 2 here. That's going to be important because when we use this guy, this t alpha over 2, what we need to look this value of t up from a t distribution chart. That's what we're going to do. But whenever you do that, you have to know what the value of alpha is, what the value of the level of significance of your problem is, but you also need to know degree of freedom. So you're going to use the table to find this value, but the degree of freedom that you use when you look it up is going to be n minus 2. And that kind of ties in with it being n minus 2 right here. All right. So I think that's enough now to kind of get the basic idea, and I want to kind of stop here and we'll go on to the next section and we can pick it apart as we calculate an actual problem. It's going to be a little bit easier. But the bottom line is, to get this margin of error, you're going to have sample sizes thrown in here. You're going to have the point that you care about, figuring out what's happening in the population, like 8 years old or whatever right there. This is the average of the X data. This is X squared summed all together. This is the sum of X and then squared. You calculate everything under here, you take the square root, then you multiply by the standard error of the estimate, which you can find yourself, or you can just get the value from Excel and multiply it times that. Then you have to get the value from a t distribution table. This is the value of t with an area of alpha over 2 to the right. And remember, alpha is the level of significance, because all this stuff is dependent upon how sure you want to be. If your 95% level confidence level is 95%, then alpha is 0.05, but you're not finding t alpha, you're finding t alpha over 2, so you would divide the alpha level by 2 and look in the table to give you the value of t with that area to its right. We're going to do all of that as we solve a problem. You get this value of t, multiply all this stuff together, it'll give you a margin of error. Then what you do, now that you know what the margin of error is you go back to your regression line and you say, what's the value on this line at 8 years old? That's the point I care about. You get the value from this line, that's what we're calling y hat, and to that you add the margin of error you calculated, take the same number from your line, subtract the margin of error that you just calculated, and then that's going to form an interval right here. That's going to be a lower bound and an upper bound. This interval says, for example, we might say that we're 95% confident that the population of all homeowners that have 8-year-old homes is going to give us an answer between this and this for the number of repairs per year that their home has. And we're 95% sure that all respondents are going to fall between these values. That is the power of statistics. By taking a small subset of data, calculating a regression line, doing calculations, and figuring out what millions of people might say. Even though you can't really ask them all, you can get a pretty good idea of what the range of their answers will be, and that's what we're doing here. I think that's enough talking. the point of it is to find this interval that you're 95% or 98% sure of. And then what we're going to do is we're going to solve an actual problem. We're going to solve this exact problem with the age and the number of years and all that stuff as we go forward. So make sure you understand this. Play it a couple times if you need to. Follow me on to the next lesson. We'll jump into Excel and we'll actually calculate this. And it'll all become clear once we have some numbers to play around with.
Learn anything at mathandscience.com.